Somewhere beneath our feet, buried under layers of rock laid down over millions of years, there may be clues that challenge something we've always taken for granted. We've long assumed that humans are the first species on Earth to build technology, the first to shape metal, burn fossil fuels, split atoms, and change the planet itself. But in 2018, two scientists asked a simple, unsettling question. What if we're not the first? What if other industrial civilizations existed on Earth long before humans, and time erased almost everything they made? And if that were true, would we even know what to look for? When we think about Earth's history, our minds tend to compress time in ways that distort our perception. Human civilization, in its current industrial form, has existed for roughly 300 years. Anatomically, modern humans have been present for perhaps 300,000 years. These numbers feel substantial until we place them against Earth's actual age of 4.5 billion years. To put this in perspective, if Earth's entire history were compressed into a single 24-hour day, human industrial civilization would occupy the last tenth of a second before midnight. Everything we've built, every technological achievement, every city and monument exists in a time span so brief it barely registers on the geological clock. This compression of time creates an important challenge for scientists. The fossil record, despite its richness, represents an incomplete chronicle of life on Earth. Fossilization itself is a rare event that requires specific conditions. An organism must die in the right place, at the right time, with the right surrounding chemistry to preserve its remains. Soft tissues decay rapidly, leaving behind only bones, shells, or in rare cases, impressions of structures that once existed. Even when conditions align perfectly, the fossil must then survive millions of years of geological activity. The grinding movements of tectonic plates, the erosion of mountains, the flooding of ancient seas, the chemical transformations that occur as rock layers shift and change. Consider what this means for detecting evidence of ancient civilizations. Dinosaurs dominated Earth for approximately 180 million years, an expanse of time that dwarfs human existence by factors of thousands. Yet despite this enormous temporal footprint, paleontologists have recovered only a few thousand near-complete dinosaur specimens. The vast majority of species that lived during the Mesozoic era left no fossil record whatsoever. If creatures that walked Earth for tens of millions of years can vanish almost entirely from the geological record, what hope would there be of finding evidence of a civilization that might have lasted only thousands or tens of thousands of years? The problem becomes even more acute when we consider the nature of technological artifacts. Buildings, roads, tools, and machines are all subject to weathering and decay. The oldest continuously exposed surface on Earth is found in the Negev Desert in southern Israel, dating back just 1.8 million years. Everything older exists either buried beneath younger rock, exposed only through erosion or human excavation, or has been completely destroyed through geological recycling. The ocean floor, where one might expect sediments to accumulate and preserve evidence, is relatively young by geological standards. Oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones, meaning that no part of the modern ocean floor is older than about 170 million years. In 2018, physicist Adam Frank and climate scientist Gavin Schmidt published a paper exploring these challenges in formal scientific terms. Their work began with a conversation about how we might detect alien civilizations through their impact on planetary climate, but quickly evolved into something more provocative. If humans have only existed in our current form for 300,000 years and have possessed industrial technology for a mere 3 centuries, would evidence of our civilization be detectable millions of years from now? More intriguingly, if another industrial civilization had existed on Earth in the deep past, would we be able to recognize the traces they left behind? They named their thought experiment the Silurian hypothesis, borrowing the term from a fictional species in the television series Doctor Who. The Silurians of that show were reptilian beings who had built an advanced civilization on Earth millions of years before humans evolved. While Frank and Schmidt were careful to emphasize that they didn't believe such civilizations had actually existed, they recognized that asking the question in rigorous scientific terms could reveal important insights about both astrobiology and our own impact on the planet. The fundamental question posed by the Silurian hypothesis is deceptively simple. What signatures does an industrial civilization leave behind, and how long do those signatures persist? To answer this, we need to understand what makes certain types of evidence more durable than others. Physical objects seem like they should be our best bet for detecting past civilizations. After all, we dig up ancient pottery shards, stone tools, and building foundations from human settlements that are thousands of years old. But the key word there is thousands, not millions. Stone tools from early humans persist because stone is durable, and because these artifacts are relatively recent in geological terms. Even so, the vast majority of stone tools ever made have been lost to erosion, burial, or simple dispersal. We find only tiny fractions of what once existed. Modern materials fare even worse. Concrete, one of our most ubiquitous building materials, begins deteriorating within decades when exposed to the elements. Steel corrodes rapidly without maintenance. Plastics, despite their reputation for persistence, break down into smaller and smaller fragments when exposed to ultraviolet light and mechanical weathering. Within a few thousand years, most of the structures we've built will have crumbled into unrecognizable debris. Within a few million years, even that debris will likely have been dispersed, buried, or chemically transformed beyond recognition. This is where Frank and Schmidt's analysis becomes particularly interesting. They calculated that the current urban area of Earth represents less than 1% of the planet's surface. If we imagine human civilization disappearing tomorrow, the chances of a future geologist stumbling upon the ruins of a city become vanishingly small as millions of years pass. Tectonic activity would bury some areas beneath new rock. Erosion would wear down others. Sea level changes would submerge coastal regions. The continents themselves would shift positions as plates continue their slow dance across Earth's surface. But industrial civilizations don't just build things, they also consume enormous amounts of energy, and that energy consumption leaves chemical traces that can persist much longer than physical structures. This is where the real detective work begins. Every factory, power plant, and vehicle that burns fossil fuels releases carbon dioxide into the atmosphere. This carbon has a specific isotopic signature because it comes from organic material that was buried millions of years ago. Ancient plants pulled carbon dioxide from the atmosphere through photosynthesis, preferentially incorporating carbon-12 over its heavier cousin, carbon-13. When we burn coal, oil, or natural gas, we release this ancient, isotopically light carbon back into the air. This creates a measurable change in the ratio of carbon-13 to carbon-12 in the atmosphere. That change gets recorded in tree rings, in ice cores, in marine sediments, and in any number of other geological repositories. Scientists examining these records in the future would see a sharp shift in carbon isotope ratios beginning around 1750, right when the Industrial Revolution started ramping up. This shift is so distinct and so rapid in geological terms that it would stand out clearly even millions of years from now, assuming the sediments containing this signature survive. Temperature changes leave their own marks. As carbon dioxide levels increase, global temperatures rise, and this warming affects the isotopic ratios of oxygen preserved in carbonate minerals. Oxygen-18, a heavier isotope of oxygen, behaves differently than oxygen-16 at different temperatures. By examining oxygen isotope ratios in fossil shells and carbonate rocks, geologists can reconstruct ancient temperatures. The current warming trend, happening over mere decades and centuries, would appear as a sharp spike in these records. Agriculture contributes another signature. The use of nitrogen-based fertilizers has dramatically altered the global nitrogen cycle. Synthetic fertilizers introduce nitrogen with different isotopic compositions than natural sources, and this shows up in the geological record. Increased soil erosion from farming and deforestation sends more sediment into the oceans, changing the composition and accumulation rate of marine sediments. Mining and industrial processes have scattered specific elements across the planet in patterns that don't occur naturally. Lead from leaded gasoline, for instance, shows up in ice cores and sediments worldwide. Chromium, platinum, gold, and other metals associated with industrial processes have been dispersed far beyond their natural concentrations. These metal anomalies would be detectable long after the factories that produced them have crumbled to dust. Then there are substances that simply don't exist in nature. Synthetic organic compounds like PCBs and certain plastics have molecular structures that natural processes don't produce. Even as these materials break down over time, their degradation products might retain chemical signatures indicating artificial origin. The question is how long these signatures remain recognizable, a topic that's still being actively researched. Perhaps most persistently, nuclear activity creates isotopes that serve as almost perfect markers of technological civilization. Natural uranium contains 3 isotopes: uranium-238, uranium-235, and trace amounts of uranium-234. Nuclear fission preferentially uses uranium-235, leaving behind fission products with distinctive isotope ratios that don't occur in natural deposits. The Oklo natural nuclear reactors in Gabon, Africa, provide a fascinating example of how such signatures persist. 2 billion years ago, natural processes created sustained nuclear chain reactions in uranium ore deposits. The evidence for these ancient reactors is still clearly visible in the isotope ratios of uranium and its fission products, despite 2 billion years of geological change. Modern nuclear weapons and reactors produce even more distinctive signatures, including transuranic elements like plutonium and curium that don't occur naturally on Earth at all. Plutonium-244 has a half-life of roughly 80 million years, while curium-247 has a half-life of 15 million years. If a technological civilization used nuclear weapons or built nuclear reactors, traces of these elements could potentially remain detectable for a substantial fraction of Earth's history. With this understanding of what industrial activity might leave behind, Frank and Schmidt turned their attention to Earth's actual geological record to see if anything resembling these signatures appeared in the deep past. What they found was both intriguing and humbling. The geological record contains numerous events that, at first glance, look suspiciously similar to what an industrial civilization might produce. But the key phrase there is "at first glance." None of these events provide clear evidence of past technological societies, but they do demonstrate how difficult it can be to distinguish between natural processes and hypothetical industrial signatures. The most striking example is the Paleocene-Eocene thermal maximum, often abbreviated as PETM, which occurred roughly 56 million years ago. During this event, global temperatures increased by between 5 and 7 degrees Celsius over a period of about 200,000 years. That might sound slow, but in geological terms it's remarkably rapid. Carbon dioxide levels spiked dramatically. The oceans became more acidic. Species went extinct while others flourished in the changed conditions. The isotopic signatures in rocks from this period show patterns eerily similar to what we're creating right now through industrial fossil fuel combustion. Scientists have proposed various explanations for what caused the PETM. One leading hypothesis involves the expansion of igneous rock in the North Atlantic region into organic-rich sediments. As hot magma came into contact with these sediments, it would have heated the organic material, driving off enormous quantities of carbon dioxide and methane. This North Atlantic igneous province eventually became Iceland and related geological formations. The timescale, the carbon signatures, the temperature spike, all of these align with this volcanic hypothesis, but they also align, uncomfortably well, with what a civilization burning massive amounts of fossil fuels might produce. Other mysterious events pepper the geological record. The end Permian extinction, also called the Great Dying, occurred about 252 million years ago. It was the most severe extinction event in Earth's history, wiping out roughly 90% of marine species and 70% of terrestrial vertebrates. The event coincides with massive volcanic eruptions in Siberia, but it also shows rapid changes in carbon isotope ratios, ocean chemistry, and atmospheric composition that resemble, at least superficially, what massive industrial activity might cause. These comparisons don't suggest that ancient civilizations caused these events. The volcanic explanations are well supported by multiple lines of evidence, but they do illustrate a crucial point. Natural processes can produce signatures that look very similar to industrial activity. This creates what Frank and Schmidt call detection problem. If we found evidence that looked like industrial signatures in ancient rocks, how would we distinguish it from natural geological events? Here's where the Silurian hypothesis presents an interesting paradox. The longer a civilization lasts, the more evidence it should leave behind. A society that persists for millions of years would have far more opportunity to leave its mark on the geological record than one that lasts only thousands of years. But a civilization that lasts for millions of years probably needs to be sustainable. It would need to develop renewable energy sources, circular material economies, and technologies that work in balance with natural systems rather than against them. A sustainable civilization would leave far fainter geological traces than one burning through fossil fuels and mining metals at unsustainable rates. Wind and solar power don't release ancient carbon into the atmosphere. Recycling reduces the need for mining. Sustainable farming practices minimize soil erosion. In other words, the civilizations most likely to persist for very long periods would be the hardest to detect in the geological record. This creates a kind of observational bias. If we're looking for signatures of past civilizations, we're most likely to find evidence of short-lived, unsustainable ones, precisely because those are the civilizations that would have burned the brightest before collapsing. Long-lived, successful civilizations might have existed without leaving clear traces for future geologists to find. We might be, as Frank and Schmidt note, looking for the wrong things in the wrong places. From here, the story becomes less about solving a puzzle and more about slowly observing what these discoveries suggest when viewed over time. Among all the signatures an industrial civilization might leave behind, few are as ubiquitous in modern life as plastic. We produce hundreds of millions of tons of plastic every year, and much of it ends up in the environment. Microplastic particles have been found everywhere, from Arctic ice to deep ocean trenches to the tissues of living organisms across the globe. These particles are durable in ways that few other human creations can match. Plastic doesn't biodegrade in any conventional sense. It photodegrades, breaking down into smaller and smaller pieces when exposed to ultraviolet light. But the molecular chains that make up plastic polymers resist the kinds of biological and chemical processes that would break down natural materials. In deep ocean sediments or in frozen environments, plastic could remain virtually unchanged for hundreds of thousands, possibly millions of years. This makes plastic an ideal geological marker. Future scientists examining Earth's sediment layers would discover a sharp transition where plastic particles suddenly appear in enormous quantities. This layer would mark the beginning of what some geologists have started calling the Anthropocene epoch, the age when humans became a geological force capable of leaving permanent traces in the rock record. But plastic is a recent invention, appearing in large quantities only in the mid-20th century. If we're looking for evidence of ancient civilizations, we need to ask whether similar durable synthetic materials might have been created by earlier societies. The answer is that we don't really know what to look for. Our plastics are based on petroleum, but there's no reason to assume that another civilization would have developed the same chemistry. They might have created entirely different synthetic materials, with different molecular structures and different degradation pathways. Some researchers have begun examining sediment cores with this question in mind, looking for anomalous particles that don't match any known natural or modern synthetic material. So far, no clear candidates have emerged, but the search is hampered by the fact that we're not entirely sure what we're searching for. An advanced material designed to be durable might look unusual when examined under a microscope, but unusual doesn't necessarily mean artificial. Nature produces its own share of strange molecular structures. Nuclear technology provides perhaps the clearest potential signature of advanced civilization. The isotopes produced by nuclear fission and fusion reactions are distinctive, and in some cases have no natural sources on Earth. If we found, say, plutonium-244 or curium-247 in ancient rock layers, we would have to seriously consider the possibility that someone had been conducting nuclear reactions. The oclonatural reactors demonstrate that fission can occur without technology, under very specific geological conditions. About 2 billion years ago, uranium deposits in what is now Gabon had just the right concentration and configuration to sustain nuclear chain reactions. Groundwater flowing through the deposits acted as a moderator, slowing neutrons enough to sustain fission. These reactions ran intermittently for hundreds of thousands of years, consuming uranium and producing fission products. We can identify the oclo-reactors through their distinctive isotope signatures. The uranium is depleted in uranium-235, the fissile isotope, compared to natural uranium. The surrounding rocks contain elevated levels of certain elements that are characteristic fission products. But crucially, the oclo-reactors didn't produce transuranic elements in significant quantities. The reactions weren't energetic enough or sustained enough to create elements heavier than uranium, in amounts that would persist to the present day. Artificial nuclear reactions, on the other hand, routinely produce transuranic elements. Nuclear weapons create a flash of isotopes including plutonium and americium. Nuclear reactors produce a different mix depending on their design, but all produce some amount of transuranic materials. If these materials were dispersed into the environment in sufficient quantities, their decay products might be detectable millions of years later. This raises an intriguing possibility. If we found evidence of transuranic elements in ancient sediments, with isotope ratios that couldn't be explained by natural processes, it would be compelling evidence of past nuclear technology. So far, no such evidence has been found, but it's worth noting that we've only examined a tiny fraction of Earth's rock record. Deep ocean sediments, polar ice cores, and rocks from different geological periods could potentially hold surprises we haven't discovered yet. One of the challenges in evaluating the Silurian hypothesis is that we still don't fully understand many aspects of Earth's geological history. The further back in time we look, the less complete our knowledge becomes. Rock layers get buried, transformed, or destroyed. The fossil record becomes sparser. The chains of reasoning connecting observations to conclusions grow longer and more uncertain. Consider the Cambrian explosion, a period roughly 540 million years ago, when complex multicellular life seems to have appeared suddenly in the fossil record. Before this event, we find mostly simple organisms, single cells, and basic multicellular forms. After it, we find a bewildering variety of complex animals with eyes, shells, sophisticated body plans, and behaviours. Traditional evolutionary theory suggests this transition should have taken tens of millions of years of gradual change. Instead, it seems to have happened over a period of perhaps 20 to 30 million years, a mere instant in geological time. Various hypotheses have been proposed to explain the Cambrian explosion. Changes in ocean chemistry might have enabled the formation of hard shells and skeletons, which fossilise much more readily than soft tissues. Rising oxygen levels might have provided the energy needed for complex metabolism and active lifestyles. Ecological factors like predator-prey relationships might have driven rapid evolutionary innovation. But there's another possibility that the Silurian hypothesis raises, however speculatively. What if some of these rapid transitions in the fossil record coincide with periods when civilizations were actively modifying their environment? not necessarily creating new species, though biotechnology isn't beyond imagination, but rather changing conditions so dramatically that ecosystems had to rapidly adapt or perish. This is pure speculation, of course. There's no direct evidence linking the Cambrian explosion or any other biological event to technological civilization. But it serves as an example of how the Silurian hypothesis can prompt us to think differently about patterns we see in Earth's history. Some of these patterns might have explanations we haven't considered, because we've always assumed we were the first technological species. One of the most thought-provoking aspects of the Silurian hypothesis is how it reframes our relationship with the geological record. Every textbook on Earth history discusses mass extinctions, climate shifts, and biogeochemical cycles. We have explanations for many of these events, explanations involving volcanic eruptions, asteroid impacts, changes in ocean circulation, and other natural processes. These explanations are generally well supported by evidence, but the Silurian hypothesis asks us to consider whether we would recognize signatures of industrial activity even if they were present. Are we perhaps looking at evidence of ancient civilizations and interpreting it as natural because we assume natural explanations are the only possibilities? This doesn't mean we should abandon well-established geological theories in favor of speculation about ancient civilizations. Science works by preferring simpler explanations over more complex ones, when both fit the evidence equally well. Volcanic eruptions are a simpler explanation for the PETM than hypothetical civilizations, but it does mean we should remain open to the possibility that our interpretations might be incomplete. There's a parallel here to the search for life elsewhere in the universe. For decades, astrobiologists have been developing techniques to detect biosignatures, atmospheric compositions or surface features that might indicate the presence of life on other planets. But these techniques are based on life as we know it on Earth. We look for oxygen and methane in atmospheres because those are the gases that biology produces here. We search for liquid water because that's the solvent life uses on our planet. But what if life elsewhere uses different chemistry? What if it's based on silicon instead of carbon, or uses ammonia instead of water? We might be looking right at evidence of alien biology and not recognizing it because it doesn't match our expectations. The Silurian hypothesis raises a similar question about technosignatures. We know what modern human industrial activity looks like, but would we recognize the signatures of a civilization that used different technologies or operated on different timescales? As we move deeper into this exploration, the questions become less about specific answers and more about the nature of deep time itself. Earth's history spans 4.5 billion years. Human written records extend back perhaps 5,000 years. Our species has existed for 300,000 years. The entire history of complex life on land covers roughly 400 million years. These numbers are difficult to hold in our minds simultaneously. We evolved to think in terms of days, seasons, and lifetimes. Geological time operates on scales so vast that they resist intuitive understanding. 1 million years sounds like a long time, but it represents only 1/4000th of Earth's total history. Events separated by 1 million years, which would be impossible to distinguish in most parts of the geological record, could contain the entire rise and fall of civilizations. This temporal resolution problem creates fundamental limitations on what we can know about the deep past. Even under ideal preservation conditions, the geological record averages out events. A layer of sediment might represent 1,000 years of accumulation, compressing everything that happened during that millennium into a single thin band of rock. Rapid changes that unfold over decades or centuries can look instantaneous in the geological record. Slow changes that take hundreds of thousands of years might be almost invisible. This averaging effect means that we can identify major events like asteroid impacts or volcanic eruptions, which leave distinctive widespread signatures. But more subtle influences, including the activities of technological civilizations, might blur together with natural variability. We see the big picture, the overall trends and dramatic transitions, but the fine details are often lost. And with that thought resting quietly in the background, we can consider what this means for our own legacy. If future geologists examine rock layers from our current era, tens of millions of years from now, what will they find? Based on the analysis by Frank and Schmidt, the answer is that human industrial civilization will have left a clear and distinctive mark, but perhaps not in the ways we might expect. Our cities, the concrete and steel monuments to our technological prowess, will likely have vanished. A few scattered artifacts might remain, buried in unlikely places by chance, but nothing that would definitively prove the existence of a global civilization. Instead, the evidence will be chemical and biological. The carbon isotope signature will be unmistakable. A sharp spike in isotopically light carbon, corresponding to the burning of fossil fuels, will mark the beginning of the Industrial Revolution. This spike will correlate with temperature increases visible in oxygen isotope ratios. The combination of these signatures, happening simultaneously on a global scale, would be difficult to explain through purely natural processes. Nitrogen isotope ratios will show evidence of synthetic fertilizer use. Soil erosion rates will have increased, visible in increased sedimentation in ocean basins. Metal concentrations in sediments will show anomalies corresponding to mining and industrial pollution. The extinction of large mammals and the proliferation of commensal species like rats and mice will create a distinctive pattern in the fossil record. And then there are the materials that will persist longest: plastics and nuclear waste. Microplastic particles will be embedded in sediment layers worldwide, creating a marker horizon that future geologists couldn't miss. Radioactive isotopes from nuclear weapons testing and nuclear power generation will provide additional evidence of technological activity. But here's the interesting question: how long will this signature remain readable? Plastics break down over time, though the timescale for complete degradation is still uncertain. Radioactive isotopes decay according to their half-lives, becoming undetectable after several half-lives have passed. Carbon isotope anomalies can be obscured by later geological events. The longer we look into the future, the fainter our signature becomes. Frank and Schmidt estimate that the clearest evidence of human industrial civilization would be detectable for perhaps a few tens of millions of years. After that, the signals start to fade into the noise of natural variability. 100 million years from now, a geologist might notice some anomalies in the rock record, but might attribute them to unusual volcanic activity or other natural causes. 200 million years from now, most traces of our civilization would be difficult to distinguish from background variation. This raises a sobering point. If we can only reliably detect our own civilization in the geological record for a few tens of millions of years, then the detection window for any hypothetical previous civilization is similarly limited. Earth is 4.5 billion years old. If a civilization arose and fell 200 million years ago, we might not be able to find clear evidence of it, even if we knew exactly when and where to look. If one existed 500 million years ago, the evidence would be even more degraded. And if multiple civilizations rose and fell at different points in Earth's deep past, most of them would be completely invisible to us. This is where the Silurian hypothesis takes an interesting turn toward astrobiology. If detecting ancient civilizations on Earth is difficult because of geological recycling and erosion, what about looking elsewhere in the solar system? The Moon has no atmosphere and no tectonic activity. Its surface is geologically dead, which means that anything placed on the lunar surface would remain there, essentially unchanged for billions of years. If a technological civilization arose on Earth millions of years ago and had the capability to travel to the Moon, any artifacts they left there would still be present, protected from the weathering and geological processes that would have erased them on Earth. Mars presents a similar opportunity. The planet was once much wetter and warmer than it is today, with liquid water on its surface and possibly a thicker atmosphere. If Mars ever hosted indigenous life, or if that life ever evolved to technological capability, evidence might still be preserved in Martian rocks and sediments. Mars has less geological activity than Earth, with no plate tectonics and minimal erosion in its current dry state. Signatures that would have been destroyed on Earth might persist on Mars. This thinking extends to the search for life and civilization beyond our solar system. When we look at exoplanets and try to identify biosignatures or technosignatures, we're implicitly assuming that we'll catch civilizations in the act of being active. But what if most technological civilizations are short-lived? What if they typically last only thousands or tens of thousands of years before collapsing or transitioning to something else? The geological record on those planets might be full of signatures from multiple past civilizations, but we'd only detect them if we could examine the surfaces closely. From light years away, looking at atmospheric spectra, we might only see the faintest hints or nothing at all. This suggests that the search for intelligence in the universe might be more challenging than we thought, not because intelligence is rare, but because its signatures might be fleeting on cosmic timescales. At its core, the Silurian hypothesis is less about whether ancient civilizations actually existed, and more about the nature of evidence itself. It asks us to consider what we can and cannot know about deep history, and how we might expand the limits of that knowledge. Science proceeds by examining evidence and constructing explanations that fit the observations, but the evidence available to us is always incomplete. The geological record is a book with most of its pages missing. The pages that remain are often smudged, torn, or written in languages we're still learning to read. We do our best to reconstruct the story from these fragments, but we have to acknowledge the gaps in our understanding, and the Silurian hypothesis suggests that some of those gaps might contain surprises. It doesn't claim that ancient civilizations did exist, but it raises the possibility that they could have existed without our knowledge. This possibility, however remote, should make us more humble about our conclusions and more curious about anomalies in the data. It also highlights the importance of looking for evidence in new ways. Traditional paleontology looks for bones and shells. Geology looks for minerals and rock formations. But if we want to detect ancient industrial activity, we might need to develop new techniques focused on subtle chemical signatures, unusual isotope ratios, or synthetic materials that don't fit natural patterns. Some researchers are already exploring these directions. Geochemists are analysing sediment cores with greater precision than ever before, looking for trace elements and isotope anomalies that might have been overlooked in earlier studies. Astrobiologists are developing techniques to detect technosignatures on other worlds, methods that could potentially be applied to Earth's own geological record. There's something both humbling and expansive about viewing Earth's history through the lens of the Silurian hypothesis. Humbling because it reminds us how brief our own tenure has been, how little we truly know about the deep past, and how easily our own civilization could vanish from the geological record given enough time. Expansive because it opens up possibilities we might not have considered. Questions about the nature of intelligence, technology, and time that go beyond our usual frameworks. We often think of human history as a story of progress, of gradual advancement from primitive beginnings toward increasing sophistication. But what if history is more cyclical? What if technological civilizations naturally have limited lifespans, rising from the energy resources available to them, burning through those resources, and then either collapsing or transitioning to more sustainable forms that leave fainter traces? If that's the pattern, then Earth might have hosted multiple such cycles, separated by millions of years. Each cycle might have been different, using different energy sources, developing different technologies, leaving different signatures. We might be just the latest iteration in a long series of civilizations, each one believing itself to be the first, each one destined to leave fading traces that future civilizations might or might not recognize. This isn't to say that this is actually the case. There's no direct evidence for pre-human civilizations, and the default scientific position must be skepticism in the absence of such evidence. But the thought experiment is valuable. because it challenges our assumptions and expands our thinking about what's possible. As we consider these questions more deeply, the relationship between technology and geological visibility becomes increasingly interesting. Our current civilization is leaving a pronounced signature precisely because we're using energy and resources unsustainably. We're burning fossil fuels that took millions of years to accumulate. We're mining metals faster than geological processes can replenish them. We're spreading synthetic materials across the planet at unprecedented rates. All of this creates clear signals in the geological record, but it's also creating problems for our civilization's long-term survival. Climate change, resource depletion, and environmental degradation all threaten the stability of our society. If we continue on our current trajectory, our industrial civilization might leave a very bright but very brief signature in Earth's rocks, a thin layer of anomalous chemistry sandwiched between more normal geological processes. The alternative would be to transition to sustainable technologies, renewable energy sources, circular material economies, minimal environmental impact. These approaches would allow our civilization to persist much longer, potentially millions of years instead of thousands. But they would also leave much fainter geological traces. Future geologists might find evidence of sustained agriculture, managed forests, and stable population centers, but these would be subtle signatures easily missed or misinterpreted. This creates an interesting selection effect. When we look back in the geological record for evidence of past civilizations, we're essentially looking for unsustainable ones. The sustainable civilizations, the ones that might have lasted for millions of years in balance with their environment, would be nearly invisible using our current detection methods. We might be surrounded by evidence of successful, long-lived civilizations and never recognize it because we're calibrated to look for the signatures of rapid industrial combustion. Mass extinctions and rapid environmental changes dominate the geological record. These events stand out because they're dramatic, because they leave clear, widespread signatures, and because they fundamentally reorganize the biosphere. The asteroid impact that ended the Cretaceous period, the volcanic eruptions that triggered the Permian extinction, the glaciation events that marked the ice ages. These are the landmarks we use to navigate deep time. But what causes these events? The asteroid impact is clear enough, but many mass extinctions and climate shifts don't have obvious single causes. They seem to result from combinations of factors: volcanic activity, ocean circulation changes, atmospheric chemistry shifts, all happening within relatively short time windows. Could some of these events have been triggered or amplified by technological civilizations? Not necessarily through intentional action, but as a consequence of industrial activity that pushed Earth's systems past critical thresholds. We know from our own experience that burning fossil fuels at scale can alter global climate. We know that nuclear weapons can affect atmospheric chemistry and create radioactive fallout. We know that damming rivers, clearing forests, and extracting groundwater can change regional and even global hydrology. If a previous civilization had undertaken similar activities at sufficient scale, they might have inadvertently triggered climate shifts or extinction events. The geological record would show the environmental changes, but attributing them to technology rather than purely natural causes would be difficult without additional evidence. This is speculation, of course. There's no proof that any historical extinction event involved technological civilizations, but it's worth considering that our current impact on the planet might not be unique. We might be following a pattern that has played out before: civilizations rising, consuming resources unsustainably, triggering environmental changes that threaten their own survival, and potentially collapsing as a result. If the Silurian hypothesis has practical value, it might be in how it focuses our attention on the long-term consequences of our actions. By thinking about what future geologists would find in rocks formed during our era, we're forced to confront the permanence of our impact. The carbon we're releasing doesn't just warm the climate temporarily and then disappear. It gets incorporated into ocean chemistry, into soil carbon pools, into the tissues of living organisms, and eventually into sedimentary rocks where it will remain for millions of years. The plastics we're dispersing will become a permanent marker horizon. The isotopes from nuclear weapons testing will persist for geological timescales. Even if our civilization collapses tomorrow, these signatures will remain, testimony to our brief but consequential presence. This long-term perspective might encourage more sustainable approaches. If we think in terms of centuries or millennia instead of quarters and years, the calculus of decision-making changes. Actions that make economic sense on short timescales might look irresponsible when viewed from the perspective of geological time. Technologies that maximize short-term profit might appear as existential threats when we consider their long-term consequences. The Silurian hypothesis also suggests that if we want our civilization to persist, we need to transition from a strategy of rapid resource consumption to one of sustainable equilibrium. The civilizations most likely to survive for millions of years would be those that learn to operate within planetary boundaries, that develop technologies compatible with long-term ecological stability, and that make decisions with distant future generations in mind. Despite all our scientific advances, despite our ability to read isotope ratios and reconstruct ancient climates, there are fundamental limits to what we can know about Earth's deep history. Some information is simply gone, erased by the relentless processes of geology. Some potential evidence might exist but remain undiscovered because we don't know where to look or what to look for, and some patterns we observe might have multiple possible explanations that we can't distinguish between with available evidence. The Silurian hypothesis lives in this realm of uncertainty. It's not a claim that ancient civilizations existed, but rather an exploration of the boundaries of knowledge. It asks what evidence would survive, where we might find it, and whether we would recognize it if we did. These are good scientific questions, even if the answer turns out to be that no such civilizations ever existed. What makes these questions valuable is that they push us to think more carefully about detection methods, about preservation biases, and about the assumptions underlying our interpretations of geological data. Even if we never find evidence of ancient civilizations, the process of looking seriously for such evidence might reveal other important insights about Earth's history. We might discover new types of natural geological processes that produce signatures resembling industrial activity. We might develop better techniques for extracting information from degraded or ambiguous evidence. We might identify new potential biosignatures or technosignatures that would be useful in the search for life beyond Earth. The questions themselves are valuable regardless of the specific answers we find. There's a meditative quality to thinking about deep time, to imagining Earth's surface transforming over millions of years, continents drifting, mountains rising and eroding away, oceans opening and closing. Our entire recorded history fits into the last few thousand years, a blink in this vast progression. Everything we consider ancient, the pyramids, the classical civilizations, the first agricultural societies, all of it exists in the most recent layers of sediment, indistinguishable from the present in geological terms. Before humans, there were the other great apes, the hominids who shaped tools and controlled fire. Before them, the diverse mammals of the Cenozoic. Before them, the age of dinosaurs spanning the Mesozoic. Before them, the rise of complex life in the Paleozoic. Before that, billions of years when life was mostly microscopic. And before even that, the hostile young Earth forming from the solar nebula. Each of these eras had its own rhythms, its own patterns of evolution and extinction, its own climate cycles and geological events. We've mapped out the general sequence, identified the major transitions, explained many of the key mechanisms, but the details remain fuzzy, especially as we look further back in time. Could there have been other intelligent species in that vast history? Possibly. The evolutionary path that led to human intelligence required many unlikely steps, but given enough time, unlikely events become probable. The real question is whether any hypothetical intelligent species would have developed technology at industrial scales, and whether they would have lasted long enough to leave detectable traces. Most species that ever existed left no fossil record at all. Of those that did fossilize, we have only tiny fractions of their populations represented. Intelligence might be rare, and industrial civilization even rarer. The window of time during which a civilization is both technological enough to leave signatures and short-lived enough to burn through resources unsustainably might be very brief. Most of Earth's history might have passed without any technological species at all, but most is not the same as all. The possibility remains, however small, that we're not the first, and even if that possibility is remote, contemplating it changes how we think about ourselves and our place in the long sweep of Earth's history. Rocks have a way of preserving unexpected information. Fossilized raindrops tell us about ancient weather patterns. Ripple marks in sandstone reveal which way ancient currents flowed. The orientation of magnetic minerals records reversals in Earth's magnetic field. Each layer of sediment is a page in a vast archive, and we're still learning how to read the language. What other information might be hidden in those layers, waiting for new techniques to reveal it? Isotope ratios we haven't measured yet. Chemical signatures we haven't identified. Patterns that would be obvious if we knew what to look for but remain invisible because we're asking the wrong questions. The history of geology is full of examples where new analytical techniques revealed unexpected information. When scientists first developed radiometric dating methods, they discovered that Earth was billions of years old, not thousands as previously thought. When they started measuring oxygen isotopes in ice cores, they revealed rapid climate fluctuations that no one had suspected. When they examined the KT boundary layer, they found the iridium signature that led to the asteroid impact hypothesis. Each new technique opens windows into the past that were previously closed. Perhaps future techniques will reveal evidence relevant to the Silurian hypothesis. Perhaps they won't. But the only way to know is to keep looking, keep developing better analytical methods, keep asking questions about what we might have missed. One of the most striking aspects of the geological record is what it doesn't contain. There are no ancient texts written in stone, no obviously artificial structures preserved from the deep past, no clear technological artifacts older than a few million years. The rocks speak through chemistry and physics, through the arrangement of minerals and the ratios of isotopes, but they don't speak in any language that resembles human communication. This absence of obvious artifacts is what makes the Silurian hypothesis so speculative. If we're looking for evidence of ancient civilizations, we need to rely on indirect signatures, chemical and biological traces that might have multiple explanations. We can't point to a preserved city or a fossilized machine and say, here is the proof. Instead, we have to look at patterns in isotope ratios, anomalies in sediment composition, and transitions in the fossil record, all of which could potentially be explained by natural processes. This evidential challenge is part of what makes the hypothesis interesting. It forces us to think carefully about what constitutes proof, about how we distinguish signal from noise, about the difference between suggestive patterns and definitive evidence. Science works by making observations, forming hypotheses, and testing those hypotheses against evidence. But what do we do when the evidence is ambiguous, when multiple hypotheses could explain the same observations? The answer is that we gather more data, develop better analytical techniques, and remain appropriately uncertain while the evidence remains ambiguous. We don't claim knowledge we don't have, but we also don't close our minds to possibilities just because they seem unlikely. The history of science is full of discoveries that seemed impossible until evidence forced us to accept them. Looking at Earth's history through the lens of the Silurian hypothesis invites us to think about cycles. Not just the familiar cycles of ice ages and warm periods, or the cycles of mass extinctions and radiations, but potentially cycles of civilization itself. If industrial civilizations naturally have limited lifespans, And if Earth's resources can support such civilizations multiple times, given enough recovery time between them, then we might expect a pattern: rise, peak, collapse, recovery, rise again. Each cycle separated by millions of years, each one potentially using different energy sources or developing along different technological paths. This pattern wouldn't be coordinated or intentional, it would simply be the result of how technological civilizations interact with finite resources and complex environmental systems. They rise when conditions permit, they consume available resources, they impact their environment. Eventually, they either collapse under the weight of their own environmental changes or transition to more sustainable forms. The geological record might preserve hints of these cycles, but distinguishing them from natural cycles would be difficult. Climate oscillations, carbon cycle perturbations, and biodiversity changes happen for many reasons. Attributing any particular event to hypothetical ancient civilizations without additional supporting evidence would be premature. Still, the conceptual framework is useful. It reminds us that our current trajectory, burning through fossil fuels accumulated over millions of years, is not sustainable on geological timescales. It suggests that if we want our civilization to persist, we need to break the pattern, to transition to technologies and practices that can continue indefinitely without depleting resources or degrading the environment. As we sit with these ideas, letting them settle into a quieter space of contemplation, what becomes clear is not a definitive answer about whether ancient civilizations existed, but rather a deeper appreciation for the boundaries of knowledge. We know a great deal about Earth's history. We've mapped out the major geological periods, identified key evolutionary transitions, explained many of the mechanisms that drive planetary change. But our knowledge is incomplete, and will always be incomplete. The further back we look, the less certain we become. The fossil record thins out. The rock record becomes more fragmentary. The chain of inference connecting observation to conclusion grows longer and more uncertain. In this space of uncertainty, the Silurian hypothesis asks us to remain open to possibilities we might not have considered. Not to accept wild speculation as fact, but to acknowledge that our current understanding might be incomplete in ways we haven't yet recognized. To remember that absence of evidence is not always evidence of absence, especially when the evidence we're looking for might be subtle, degraded, or disguised as natural phenomena. This kind of thinking is valuable not because it leads to definitive conclusions, but because it keeps our minds flexible and curious. It prevents us from becoming too confident in our interpretations, too certain that we've explained everything there is to explain. It reminds us that the universe is full of surprises, and that some of those surprises might be hidden in the rocks beneath our feet. Perhaps the most practical value of the Silurian hypothesis lies in what it tells us about our own future. By thinking about how our civilization will appear in the geological record millions of years from now, we gain perspective on the significance and permanence of our actions. Every decision we make about energy, about resources, about technology, contributes to the signature we're creating. That signature will outlast our buildings, our art, our literature, even our species. Long after everything we consider important has turned to dust, the chemical traces of our industrial activity will remain embedded in rock. This realization can be sobering, but it can also be motivating. If we're creating a permanent record, whether we intend to or not, we might choose to make it a record of wisdom rather than excess, of sustainability rather than exploitation, of careful stewardship rather than thoughtless consumption. The question isn't just whether we'll be detectable to future geologists, though that's interesting in itself. The question is what story our geological signature will tell. Will it be a story of a civilization that recognized the limits of its resources and learned to live within them? Or will it be a story of rapid rise and collapse, a cautionary tale preserved in stone? We're writing that story now, in every ton of carbon we release, every species we drive to extinction, every irreversible change we make to Earth's systems. The Silurian hypothesis reminds us that this story will persist long after we're gone, that our legacy will be measured not in monuments or achievements, but in the chemical signatures we leave behind. And so we come to rest in a space of gentle speculation, of questions that may never have definitive answers, but remain worth asking nonetheless. Did Earth host other civilizations before ours? We don't know, and may never know for certain. The evidence that might exist is subtle, degraded, ambiguous. It could be sitting in sediment cores that haven't been analysed yet, or it could have been destroyed by geological processes millions of years ago. The honest answer is that we simply can't say with certainty either way. Would we recognise such evidence if we found it? That depends on how sophisticated our analytical techniques become, and on whether we're asking the right questions. We might develop new methods that reveal patterns we've overlooked, or we might find that the signatures have degraded beyond recognition, that deep time has erased the very traces we're seeking. Does it matter whether ancient civilizations existed? In practical terms, perhaps not. Whether we're the first or the 50th technological species on Earth doesn't change the challenges we face now, but in a deeper sense, it matters because it shapes how we understand ourselves and our relationship to deep time. It affects whether we see ourselves as unprecedented or as part of a longer pattern. It influences how we think about our responsibility to the future. These questions don't demand immediate answers. They're the kind of questions that benefit from slow contemplation, from sitting with possibilities rather than rushing to conclusions. They invite us to expand our perspective, to think in timescales that dwarf human civilization, to imagine Earth's surface transforming over eons while we occupy the briefest of moments in that vast progression. Time stretches backward further than we can easily comprehend. 4.5 billion years of Earth's history, most of it without complex life, almost all of it without intelligent observers. We exist in a thin slice near the very end of this timeline, looking backward through layers of rock that grow increasingly obscure the further we look. Somewhere in those layers might be traces of others who looked out at the world and wondered about their place in it. Or there might not be. The rocks keep their secrets well, revealing only what our techniques can extract, preserving only what geological processes haven't erased. What we do know is that we're leaving traces of our own, creating a signature that will persist long after our cities have crumbled and our technologies have been forgotten. That signature will be part of Earth's permanent record, a chapter in the planet's ongoing story. Whether anyone will be around to read the chapter millions of years from now remains uncertain. Whether they'll understand what they're reading if they do find it, equally uncertain. The future stretches forward as mysteriously as the past stretches backward, full of possibilities we can barely imagine. And in this moment, suspended between vast uncertainties past and future, we continue our investigation of Earth's history, asking questions that might never be fully answered, but nevertheless help us understand where we are and what we're doing here. The rocks wait patiently, as they have for billions of years, holding their fragmentary records of what has been. We bring our instruments and our questions, hoping to coax out a few more secrets. Sometimes we succeed, sometimes we find only deeper mysteries, but the search itself is worthwhile, regardless of what we ultimately discover. For in asking whether we're the first, we inevitably ask what it means to be here at all, what legacy we want to leave, and how our brief moment fits into the almost incomprehensible sweep of planetary time. These questions don't have easy answers. Perhaps they don't have final answers at all. But they're worth carrying with us as we move forward, making choices that will echo in stone long after we're gone, contributing our own small chapter to Earth's immense and ongoing story. When we pick up a rock, we're holding a piece of history that might span millions or even billions of years. The minerals that compose it crystallized from molten magma or precipitated from ancient seas. The grains that make up sandstone were once parts of older rocks, weathered down and carried by rivers to distant shores. Each rock is an archive. though reading the archive requires specialised knowledge and sophisticated instruments. Geologists have developed remarkable techniques for extracting information from rocks. They can determine when a rock formed by measuring the decay of radioactive isotopes trapped in its minerals. They can reconstruct the temperature and pressure conditions during formation by examining mineral assemblages. They can identify the environment where sedimentary rocks were deposited by studying grain sizes, sorting patterns, and sedimentary structures. These techniques have revealed Earth's basic chronology. We know when the continents formed, when the oceans appeared, when life began, when oxygen accumulated in the atmosphere. We've mapped out the major geological periods and identified the events that separate them. We've tracked the wandering of continents across the globe and watched mountain ranges rise and fall in the geological record. But for all this knowledge, we still encounter rocks and formations that don't fit our expectations, layers with unusual chemical compositions that don't match any known natural process, mineral assemblages that seem to require conditions we can't explain, isotope ratios that appear anomalous when compared to surrounding rocks. Most of these anomalies eventually find explanations within conventional geology. A layer with strange chemistry might represent ash from a distant volcanic eruption. An unusual mineral assemblage might indicate a brief excursion in local conditions. An isotope anomaly might result from contamination or analytical error. But occasionally, anomalies resist easy explanation. They remain puzzling even after careful study, suggesting that our understanding of geological processes might be incomplete. These are the cases that keep geologists up at night, the observations that don't quite fit into existing frameworks. The Silurian hypothesis suggests that some of these anomalies might have unconventional explanations. Not that we should immediately jump to conclusions about ancient civilizations whenever we encounter something puzzling, but that we should remain open to possibilities we might not have considered. That we should ask whether the signatures we're seeing could be explained by technological activity, not as a first resort, but as one possibility among many. Chemistry provides perhaps our best window into deep time. While physical structures erode and fossilize rarely, chemical signatures can persist for enormous spans of time, encoded in the very atoms that make up rocks and minerals. Carbon isotopes tell us about ancient photosynthesis and the cycling of organic matter through Earth's systems. Organisms preferentially incorporate the lighter carbon-12 isotope when building their tissues, leaving the environment slightly enriched in carbon-13. When organic matter gets buried and becomes coal or oil, it carries this isotopic signature with it. When that coal or oil burns, the isotopically light carbon returns to the atmosphere. This is how we can identify the Industrial Revolution in the geological record. The carbon dioxide being released has a distinctive isotopic fingerprint that marks it as coming from ancient organic matter. This fingerprint shows up in tree rings, coral skeletons, ice cores, and marine sediments, creating a global signature that correlates precisely with the rise of fossil fuel combustion. Oxygen isotopes preserve information about temperature and climate. Water molecules containing oxygen-18 evaporate slightly less readily than those containing oxygen-16, so water vapour in the atmosphere is depleted in oxygen-18 compared to ocean water. When this vapour condenses and falls as rain or snow, it carries its isotopic signature to wherever it lands. In cold climates, ice sheets build up from accumulated snow, preserving a record of past precipitation and atmospheric conditions. Marine organisms incorporate oxygen from seawater into their shells and skeletons. The ratio of oxygen-18 to oxygen-16 in these shells depends on the temperature of the water when the organism lived. By measuring oxygen isotopes in fossil shells, geologists can reconstruct ancient ocean temperatures with remarkable precision. Nitrogen isotopes track the movement of this essential element through ecosystems. Natural nitrogen has a relatively consistent isotopic composition, but synthetic fertilizers produced through industrial processes have different ratios. the spread of industrial agriculture has altered nitrogen cycling globally, a change that appears in sediment cores as a shift in nitrogen isotope ratios beginning in the mid-20th century. Sulfur isotopes reveal information about atmospheric chemistry and biological processes. Different sources of sulfur, volcanic emissions, bacterial metabolism, industrial pollution have characteristic isotopic signatures. By tracking sulfur isotopes through the geological record, scientists can identify changes in atmospheric composition and biological activity over time. These chemical tools give us extraordinary power to read the geological record, but they also reveal how complex Earth's natural systems are. Isotope ratios change for many reasons, making it challenging to attribute any particular change to a specific cause without supporting evidence from multiple independent sources. Not all evidence survives equally well. Some materials and signatures persist for billions of years, while others degrade rapidly even under favourable conditions. Understanding what preserves and what doesn't is crucial for evaluating the Silurian hypothesis. Minerals are among the most durable materials. Quartz, zircon, and other resistant minerals can survive multiple cycles of erosion, burial, and metamorphism. Zircon crystals found in ancient rocks sometimes contain even older mineral grains, survivors from rocks that no longer exist in any other form. These hardy minerals serve as messengers from the deep past, carrying information encoded in their crystal structures and chemical compositions. Organic molecules are more fragile, but some can persist for surprising lengths of time under the right conditions. Biomarkers, complex organic molecules with structures that reveal their biological origin, have been recovered from rocks over 1 billion years old. These molecules are fragmentary and heavily degraded, but enough of their original structure remains to identify them as biological in origin. DNA degrades much more rapidly. Even under ideal preservation conditions, DNA breaks down into unreadable fragments within a few million years. This sets a firm limit on how far back we can trace genetic relationships through direct molecular analysis. Everything we know about life's deeper history comes from comparative anatomy, physiology, and the occasional lucky fossil, not from genetic sequencing. Artificial materials present their own preservation challenges. Metals corrode, especially in the presence of oxygen and water. Iron exposed to the elements rusts within years or decades. Even resistant metals like gold and platinum can be altered by geological processes, dissolved by hot fluids, or scattered by erosion. Synthetic organic compounds vary in their durability. Some plastics degrade relatively quickly when exposed to sunlight and weathering, breaking down into progressively smaller fragments over centuries or millennia. Others, especially those buried in anaerobic sediments, might persist much longer. The long-term fate of many modern synthetic materials remains uncertain because we haven't had enough time to observe their degradation over geological timescales. Radioactive isotopes decay according to predictable mathematical laws, their half-lives determining how long they remain detectable. Isotopes with short half-lives, days or years, disappear quickly. Those with long half-lives, millions or billions of years, persist almost indefinitely. Intermediate half-lives create a detection window, long enough that the isotopes might survive from ancient times, but short enough that they would have mostly decayed by now. This variability in preservation creates a complex picture. Some signatures from hypothetical ancient civilizations might persist clearly, while others would have vanished completely. The evidence we might find would be fragmentary and selective, biased toward whatever materials and signatures happen to be most durable. Earth is a large planet, and we've examined only a tiny fraction of its geological record. The exposed land surface represents a small percentage of Earth's total area, and most of that surface is covered by soil, vegetation, or recent sediments. Bedrock exposures, where geologists can directly examine ancient rocks, are limited to certain regions: mountainsides, canyon walls, desert areas, and places where erosion or human excavation has removed overlying material. Ocean sediments cover vast areas and preserve continuous records spanning millions of years, but sampling them requires expensive drilling projects. The Deep-Sea Drilling Project and its successors have recovered cores from thousands of locations, but these still represent only a minute sampling of the ocean floor. Vast areas remain completely unexplored at the resolution needed to detect subtle chemical anomalies. Ice cores from Antarctica and Greenland provide exceptionally detailed climate records, but they only extend back about 800,000 years, a mere eye blink in geological terms. Older ice exists at greater depths, but it's often deformed by the flow of ice sheets, mixing layers together and making interpretation difficult. The continental geological record is even more fragmentary. Most continental rocks are sedimentary, formed from the weathering and erosion of older rocks, but sedimentary rocks are themselves subject to erosion, so the older they are, the less likely they are to survive to the present. Rocks older than 1 billion years are rare. Rocks older than 2 billion years are extremely rare. Rocks older than 3 billion years exist only in a few specially preserved locations. This sampling bias means we're looking at Earth's history through a highly fragmented lens. We have good records from some time periods and some locations, but large gaps exist in both time and space. An event that left clear signatures in one region might be completely invisible in another because the rocks that would have recorded it were never deposited, or were deposited but later eroded away, or remain buried where we haven't looked. The Silurian hypothesis forces us to confront these gaps. If we're searching for evidence of ancient civilizations, we have to acknowledge that most of the potential evidence has probably been destroyed or remains undiscovered. We're not looking for a needle in a haystack. We're looking for fragments of a needle in a haystack where most of the hay has been removed and scattered across a large field. One of the greatest challenges in identifying potential technosignatures in the geological record is that nature can produce patterns that look surprisingly similar to what technology might create. This makes it difficult to distinguish between natural events and hypothetical artificial ones. The Paleocene-Eocene thermal maximum provides the clearest example. This event shows all the hallmarks of what massive fossil fuel combustion might produce: rapid carbon release, global warming, ocean acidification, changes in biodiversity. Yet the scientific consensus attributes it to natural causes, probably volcanic activity interacting with organic-rich sediments in the North Atlantic region. The evidence supporting this natural explanation is strong. We can identify the volcanic rocks from the relevant time period. We can trace the geographic extent of the volcanic province. We can model how much carbon would have been released by the interaction between hot magma and organic sediments. The numbers match reasonably well, though some uncertainties remain. But here's the thought-provoking question. If a technological civilization had existed during the Paleocene and had burned through their available fossil fuels over a few thousand years, would the resulting signature look any different from what we see in the PETM? The carbon isotope excursion would be similar. The temperature rise would be comparable. The ecological disruption would match. Distinguishing between these scenarios would require additional evidence beyond the basic chemical signatures. Other geological events create similar ambiguities. The end Permian extinction shows rapid carbon cycle disruption, temperature spikes, and ocean chemistry changes. The Ordovician glaciation displays unusual patterns of cooling and warming. The Cretaceous Ocean anoxic events reveal periods of widespread oxygen depletion in the oceans. All of these events have well-developed natural explanations, but all of them also produce signatures that overlap with what industrial activity might create. This overlap doesn't mean we should abandon natural explanations in favour of speculative ones about ancient civilizations. The principle of parsimony suggests we should prefer simpler explanations when they fit the evidence adequately. Volcanic eruptions are a simpler explanation than hypothetical civilizations for which we have no other evidence. But it does mean we should be thoughtful about what constitutes proof. If we someday develop evidence suggesting technological activity in Earth's past, we'll need multiple independent lines of evidence converging on that conclusion. Chemical signatures alone probably won't be sufficient. We'd want to see correlations between different types of evidence, patterns that are difficult to explain through natural processes, and ideally some form of physical artifacts or structures, however degraded. Taking a step back from the specific question of detection, it's worth considering how likely it is that technological civilizations could have arisen on Earth before humans. This requires thinking about the evolution of intelligence and the conditions necessary for technology to develop. Intelligence, in the sense of complex problem-solving and flexible behaviour, has evolved multiple times in Earth's history. Cephalopods like octopuses and cuttlefish are remarkably intelligent despite having evolved along a completely different path from vertebrates. Certain birds, particularly corvids and parrots, display cognitive abilities that rival those of primates. Dolphins and other cetaceans show sophisticated social behaviours and communication. Yet none of these intelligent animals have developed anything resembling human-level technology. They don't build cities, create written language, or harness energy at industrial scales. This suggests that intelligence alone isn't sufficient. Other factors must be involved. Tool use seems to be one prerequisite. Humans aren't the only tool users. Primates, birds, and even some insects use tools. But we're the only species that has developed cumulative tool culture, where innovations build on previous innovations across generations. This requires not just intelligence, but also the ability to transmit detailed information between individuals and across time. Physical manipulation is another requirement. It's hard to imagine building complex technology without hands or some equivalent appendage capable of fine manipulation. Marine mammals might be intelligent, but their flippers limit what they can construct. Birds have solved the manipulation problem differently with their beaks and feet, but they face other constraints. Energy surplus plays a crucial role. Technology development requires time and resources beyond what's needed for immediate survival. A species struggling to meet basic nutritional needs won't have the luxury of experimental innovation. Humans benefited from learning to cook food, which made nutrients more accessible and reduced the time needed for eating and digestion, freeing up time for other activities. Social organisation matters too. Large-scale technology requires cooperation among many individuals working toward common goals. This needs sophisticated communication, social norms, and probably some form of governance. Solitary species, however intelligent, would face severe limitations in what they could accomplish. Environmental factors influence whether technology develops. Humans emerged during a period of climate variability that may have favoured adaptability and innovation. Stable environments might not provide the same evolutionary pressure for technological development. All of these factors had to align for human technology to emerge. How likely is it that they aligned at other points in Earth's history? It's hard to say with confidence. The evolutionary path to intelligence seems to have been travelled multiple times, but the path to technology has, as far as we know, been travelled only once. This might mean it's extremely rare, or it might mean we're missing evidence of previous attempts. The fossil record, for all its wonders, has significant limitations when it comes to detecting intelligent behaviour or technological activity. Fossils preserve hard parts, bones and shells, occasionally soft tissues under exceptional conditions, but they rarely preserve behaviour directly. We can infer behaviour from fossil evidence in some cases. Trackways show how animals moved. Coprolites, fossilised feces, reveal what they ate. Tool marks on bones indicate butchering or other processing. Nest structures and burrows demonstrate certain behaviours, but these behavioural fossils are far rarer than body fossils, and they require specific conditions to form and be preserved. Intelligence and technology leave even fewer traces. A species might be highly intelligent without developing any behaviours that would fossilise. Mental capabilities don't fossilise at all. We can only infer them from brain size and structure, neither of which preserve reliably. Tool use might leave traces, but only if the tools are made from durable materials and happen to be deposited in environments conducive to fossilization. Human evolution illustrates these limitations. We have reasonably good fossil records for our skeletal evolution over the past few million years. We can track changes in brain size, body proportions, and other anatomical features. But our understanding of behavioural evolution is much more fragmentary. We have some stone tools from archaeological sites, but these represent only a tiny fraction of the tools our ancestors made. Wooden tools, fibre cordage, hide containers, and countless other perishable items have vanished almost entirely from the record. If we have trouble reconstructing the complete picture of human technological development over just a few million years, imagine how much more difficult it would be to detect technology from tens or hundreds of millions of years ago. The further back we look, the less complete the record becomes. Most fossils from the Mesozoic era are fragmentary bones and teeth, soft tissues, behavioural traces, and any potential technological artefacts are almost completely absent. This doesn't mean ancient civilizations existed and left no fossil traces. It means the fossil record isn't well suited to detecting them if they did exist. We'd need to look for other types of evidence, the chemical signatures and environmental changes we've been discussing, rather than expecting to find fossilized cities or machines. Earth's climate and environment have never been static. Over geological timescales, the planet undergoes continuous change driven by multiple interacting processes. Understanding these natural rhythms is essential for distinguishing them from potential artificial influences. Orbital cycles, called Milankovitch cycles, affect the amount and distribution of solar energy reaching Earth's surface. These cycles operate on timescales of tens to hundreds of thousands of years and drive the advance and retreat of ice ages. We can identify these cycles in the geological record through rhythmic changes in sediment properties and fossil assemblages. Tectonic processes operate on longer timescales. The opening and closing of ocean basins, the collision of continents, the rise of mountain ranges, all of these affect global climate and ocean circulation. The positions of continents influence how ocean currents distribute heat around the planet, which affects weather patterns, temperature gradients, and the extent of ice coverage. Volcanic activity varies over time, influenced by tectonic processes and mantle dynamics. Major volcanic episodes release enormous quantities of carbon dioxide and other gases, temporarily warming the climate. Exceptionally large eruptions can also inject sulfur aerosols into the upper atmosphere, causing brief cooling periods. The geological record shows multiple episodes of enhanced volcanism coinciding with climate shifts and sometimes mass extinctions. The carbon cycle operates on multiple timescales. On short timescales, carbon moves between the atmosphere, oceans, and biosphere through processes like photosynthesis, respiration, and ocean-atmosphere exchange. On longer timescales, geological processes like weathering and volcanic outgassing control atmospheric carbon dioxide levels. Perturbations to this cycle, whether from volcanic events, changes in weathering rates, or biological innovations, can cause significant climate shifts. Ocean circulation patterns can change relatively quickly in geological terms, reorganizing heat distribution and affecting global climate. The formation or breakdown of oceanic gateways, changes in salinity from ice sheet growth or melting, and shifts in wind patterns can all trigger circulation changes. These reorganizations sometimes happen abruptly, producing rapid climate shifts that appear in the record as sharp transitions. All of these natural processes create variability in the geological record. The challenge for the Silurian hypothesis is distinguishing between this natural variability and signals that might indicate technological activity. Some patterns might be ambiguous, potentially explainable by either natural or artificial causes. Only with multiple independent lines of evidence could we make a strong case for technological influence. While Earth's surface is constantly recycling through geological processes, the Moon's surface is geologically dead. This makes it a potentially valuable archive for evidence that might have been erased from Earth. The Moon has no atmosphere and no plate tectonics. Nothing weathers, nothing erodes in the conventional sense. Objects placed on the lunar surface would remain there essentially forever, only gradually accumulated dust from micrometeorite impacts. A spacecraft that landed on the Moon millions of years ago would still be sitting there, slowly getting buried under a thin layer of regolith but otherwise unchanged. This permanence makes the Moon an interesting place to search for evidence of ancient spacefaring civilizations. If a technological species arose on Earth millions of years ago and developed the capability to travel to the Moon, any artifacts they left there would still be present and potentially discoverable. The lunar surface has been mapped extensively by orbiting satellites. We have high-resolution images of most of the Moon's near side and moderate-resolution images of the far side. So far, these surveys have revealed no obvious artificial structures or spacecraft. The only human-made objects on the Moon are those we know we placed there: the Apollo landing sites, various crashed or landed probes, and equipment left behind by astronauts. But the Moon is a large world, and our surveys might not have detected smaller artifacts or objects in less visited regions. Future lunar exploration, whether by humans or robots, might encounter surprising discoveries. The permanently shadowed craters near the poles, for instance, have never been visited and remain largely unmapped at high resolution. If ancient lunar artifacts exist and we eventually find them, they would provide compelling evidence for previous technological civilizations. Unlike chemical signatures or ambiguous geological patterns, a spacecraft or structure on the Moon would be difficult to explain through natural processes. The challenge would be dating such artifacts to determine when they were placed there. Mars presents another intriguing possibility. The planet was once much more Earth-like than it is today, with liquid water on its surface, a thicker atmosphere, and possibly more clement temperatures. If life ever evolved on Mars, could it have developed a technological capability before the planet's climate deteriorated? The answer depends on when Mars had habitable conditions and for how long. Current evidence suggests Mars was most habitable during its first billion years or so, roughly 3.5 to 4.5 billion years ago. After that, the planet lost most of its atmosphere, dried out, and became the cold desert world we see today. A billion years sounds like a long time, and it is. But evolution on Earth didn't produce intelligent land animals until roughly 400 million years ago, more than 4 billion years after the planet formed. Complex multicellular life took billions of years to evolve. If Martian evolution followed a similar pace, it might not have had time to reach intelligence before conditions became too harsh. On the other hand, evolution's pace isn't necessarily uniform or predictable. Under different environmental pressures, with different starting conditions, evolution might proceed faster or slower than it did on Earth. We can't rule out the possibility that Martian life, if it existed, could have developed intelligence during the planet's habitable period. If a Martian civilization existed, would we find evidence of it today? The answer is possibly, because Mars has much less geological activity than Earth. There's no plate tectonics to recycle the crust. Erosion is minimal in the current dry climate, though windblown dust does gradually reshape the surface. Objects or structures that would have been destroyed on Earth might persist on Mars for billions of years. The difficulty is that we've only explored a tiny fraction of Mars. A handful of rovers have examined a few small areas in detail. Orbital imagery covers the planet, but can only resolve features down to a certain size. Subsurface features remain largely unexplored. If Martian technological artifacts exist, they could easily be in areas we haven't yet examined. Future Mars exploration will gradually fill in these gaps. As we send more missions, land in more locations, and develop better tools for subsurface investigation, we'll get a more complete picture of the planet's history. If surprises wait to be discovered, we'll eventually find them. Even if evidence of ancient technological civilizations exists in Earth's geological record or on other worlds in our solar system, we face a fundamental challenge: recognition. Would we know technological artifacts when we see them? Human technology has a particular character shaped by our biology, our environment, and our cultural history. We build with right angles and straight lines, because those are mathematically simple and structurally efficient. We use specific materials, metals, ceramics, polymers, because those are what we've learned to manufacture. We organise our cities and infrastructure in patterns that reflect our social structures and transportation needs. But a non-human technological civilization might build very differently. Their architecture might follow different geometric principles, their materials might have different compositions, their cities might be organised in ways we wouldn't recognise as deliberate. If we encountered their artefacts, we might mistake them for natural formations because they don't match our expectations of what technology looks like. This recognition problem becomes more severe as artefacts age and degrade. A fresh technological artifact, even from an alien civilization, would probably be recognisable as artificial, because it would be organised in ways nature doesn't produce. But after millions of years of weathering and geological transformation, that organisation might be lost or obscured. The artifact might appear to be just another rock or mineral deposit. Chemical signatures face a similar challenge. We know what modern human industrial activity looks like chemically, because we're creating it now. We can measure our emissions, track our pollutants, and characterise our waste products. But if another civilization used different energy sources or manufacturing processes, their chemical signatures might not match our expectations. We might be looking at evidence of their technology and interpreting it as natural because it doesn't fit our mental model of what industrial signatures should be. This recognition problem is humbling. It suggests that evidence could exist right in front of us, and we might not realise what we're seeing. Not because we're not looking carefully, but because our conceptual frameworks don't include the possibility of what we're observing. Throughout this exploration, we've encountered a recurring theme. The assumptions we bring to our investigations shape what we're capable of seeing. When we look at the geological record, we interpret it through frameworks built on the assumption that all the patterns we observe result from natural processes. This assumption has served science well and has led to powerful explanations for Earth's history. But assumptions, however well-founded, can also blind us to alternatives. If we assume that natural processes explain everything, we might not seriously consider whether some observations might have artificial causes. We might dismiss anomalies as measurement errors or artifacts of analysis rather than investigating whether they might represent something genuinely unusual. The Silurian hypothesis doesn't ask us to abandon the assumption that natural processes dominate Earth's history. That assumption remains valid and well supported. Instead, it asks us to hold that assumption a bit more lightly, to recognise it as an assumption rather than an absolute certainty, and to remain open to evidence that might point in unexpected directions. This kind of epistemic humility is valuable in science. The history of scientific progress is full of examples where dominant assumptions were eventually overturned or significantly modified. Continental drift seemed impossible to most geologists until evidence forced them to accept it. The idea that Earth was billions rather than thousands of years old initially met fierce resistance. The concept that asteroids could cause mass extinctions was considered fringe until the evidence became overwhelming. In each case, the scientific community eventually accepted new ideas because evidence demanded it. But in many cases, the evidence had been available for years or even decades before it was properly recognised and interpreted. Observers saw the patterns but interpreted them through existing frameworks that didn't accommodate the correct explanation. The Silurian hypothesis might be completely wrong. Ancient technological civilizations might never have existed on Earth. But by seriously considering the possibility, we expand our investigative frameworks and potentially become better at recognizing patterns we might otherwise miss. As we move deeper into this contemplation, the specific question of whether previous civilizations existed begins to matter less than the broader questions it raises about knowledge, evidence, and how we understand deep time. Science is fundamentally a process of asking questions, gathering evidence, forming hypotheses, and testing those hypotheses against reality. The questions we ask shape the answers we're capable of finding. If we never ask whether ancient civilizations might have existed, we won't develop the analytical techniques that might detect them. We won't look for their signatures in the geological record. We won't recognize potentially relevant patterns when we encounter them. This doesn't mean we should ask every possible question regardless of how unlikely the answers might be. Science has limited resources, and we need to prioritize investigations with reasonable chances of yielding useful results. But it does mean we should periodically examine our assumptions and consider whether we're missing possibilities because we haven't seriously asked about them. The Silurian hypothesis serves this function. It prompts us to think about geological signatures in new ways, to consider what different types of civilizations might leave behind, to develop techniques for distinguishing natural from artificial patterns. Even if we never find evidence of ancient civilizations, these techniques might prove valuable for other purposes, studying Earth's climate history, understanding biogeochemical cycles, or searching for life on other worlds. The questions themselves have value beyond their specific answers. They stretch our thinking, challenge our assumptions, and remind us that our current understanding, however sophisticated, remains incomplete. In the end, what we're left with is silence and possibility. The geological record doesn't speak clearly about ancient civilizations. It whispers ambiguities, shows us patterns that might mean something or might mean nothing, presents us with anomalies that could be natural or could be something else. This silence is both frustrating and appropriate. If technological civilizations are rare and short-lived, we wouldn't expect them to leave loud, obvious signals spanning millions of years. We'd expect exactly what we see, a mostly natural record with occasional ambiguous patterns that resist simple interpretation. The possibility remains open, not a strong possibility supported by compelling evidence, but a logical possibility consistent with what we know about physics, geology, and evolution. The question of whether we're Earth's first technological civilization doesn't have a definitive answer yet. Perhaps it never will. But the question itself is worth asking because it reveals the boundaries of our knowledge and the limits of what we can know about deep time. When we sit with this uncertainty, when we allow ourselves to dwell in the space between knowing and not knowing, something shifts in how we perceive our relationship to time itself. We live our lives in increments of days and years, planning for decades at most, occasionally contemplating centuries when we think about historical legacy. But geological time operates on scales so vast that our entire species, from its first emergence to its eventual end whenever that might come, occupies less space than a single sentence in an encyclopedia of Earth's history. This perspective can feel diminishing at first. We build monuments intended to last forever, yet forever, in human terms, is merely a geological instant. The pyramids of Egypt, among humanity's most enduring constructions, are less than 5,000 years old. In geological terms, they were built yesterday. The entire span of recorded human history, all our civilizations and empires, all our discoveries and achievements, fits comfortably within the most recent layers of sediment still accumulating on ocean floors and lake beds. Yet there's something profound in recognizing our place within this vast temporal landscape. We're part of an ongoing process, a planet that has been generating complexity and novelty for billions of years. Life itself is roughly 3.5 billion years old, nearly as old as the solid surface we stand on. For most of that time, life was microscopic, single cells doing their patient work of capturing energy and reproducing. Then, in what seems like a sudden flourish, though it actually took hundreds of millions of years, complexity exploded into the forms we recognize. Plants and animals, ecosystems and food webs, the intricate dance of predator and prey, symbiont and competitor. We emerged from this process recently, these upright apes with oversized brains and clever hands. We learned to make fire, to shape stone, to plant seeds and domesticate animals. We built cities, developed writing, created art and music and mathematics. We split the atom, went to the moon, peered back toward the beginning of the universe itself. All of this in the evolutionary equivalent of an afternoon. And now we ask whether others might have walked a similar path before us, whether intelligence and technology have flowered on Earth before, leaving traces we haven't yet learned to recognize. The question feels audacious, almost presumptuous, as if we're projecting our own significance backward into time. But it's also a humble question in its way, acknowledging that we might not be as unique as we've assumed, that the processes that led to us might have operated before. The silence of the rocks on this question is instructive. They don't confirm our uniqueness, but they don't reveal our predecessors either. They simply present us with patterns, with chemistry and structure, with the accumulated record of processes operating over unimaginable spans of time. How we interpret those patterns says as much about us, about our assumptions and frameworks and imaginative capabilities, as it does about what actually happened in the deep past. Consider what this means for how we think about evidence itself. In our daily lives, we're accustomed to evidence being relatively straightforward. We see something happen, or we find clear traces of what happened, and we can reconstruct events with reasonable confidence. But geological evidence operates differently. It's fragmentary, transformed, often ambiguous. We're looking at effects separated from their causes by millions of years and countless intervening processes. A layer of ash in a rock formation tells us a volcano erupted somewhere, but determining exactly where and when requires careful analysis. A shift in isotope ratios indicates something changed in Earth's carbon cycle, but identifying the specific cause demands multiple lines of evidence and often remains uncertain. An extinction event preserved in the fossil record shows us that many species died, but understanding why requires piecing together clues from chemistry, climate proxies, and the timing of other geological events. This interpretive challenge becomes even more acute when we're looking for rare events or unusual processes. Natural phenomena repeat across geological time. Volcanoes erupt regularly, climates shift cyclically. Ocean chemistry varies in response to well-understood processes. These patterns create a baseline against which we can identify anomalies. But technological civilizations, if they existed at all, would be unique events, singular occurrences that don't fit into repeating patterns. How do you recognize a unique event when your methods are calibrated to identify patterns and regularities? How do you distinguish a genuine anomaly from random noise or measurement error? These are fundamental challenges in any field that deals with rare events, and they apply with particular force to the search for ancient civilizations. The silence we encounter might simply reflect the absence of such civilizations. The most straightforward explanation for not finding evidence of previous technological species is that none existed. We might genuinely be the first, the only time in Earth's long history that evolution produced a species capable of reshaping its planet through technology. But the silence might also reflect our limited ability to hear what the rocks are saying. We've only been seriously studying Earth's geological history for a couple of centuries. Our analytical techniques improve constantly, revealing information that previous generations of geologists couldn't access. Isotope geochemistry, for instance, is less than a century old as a rigorous scientific discipline. Mass spectrometry, capable of measuring tiny variations in isotope ratios, is even more recent. Each new technique opens windows into the past that were previously closed. What might we discover with techniques we haven't invented yet? What information is encoded in rocks and sediments in forms we don't currently know how to read? The history of geology suggests that each new analytical method reveals unexpected patterns and raises new questions. There's no reason to think we've reached the limit of what can be learned from Earth's rock record. This ongoing expansion of investigative capability means that questions we can't answer today might become answerable tomorrow. The Silurian hypothesis might remain speculative indefinitely, or future researchers might develop techniques that can definitively determine whether industrial signatures exist in ancient rocks. We can't predict which outcome is more likely. We can only acknowledge that our current state of knowledge is incomplete and likely to expand in unpredictable directions. The possibility that ancient civilizations existed, however remote that possibility might be, serves another function beyond the specific question it asks. It reminds us to maintain epistemic humility, to recognize that our current understanding of Earth's history, though sophisticated, remains provisional. Science doesn't offer absolute certainties. It offers the best current explanations based on available evidence, always subject to revision as new evidence emerges. This provisional nature of scientific knowledge isn't a weakness, it's a strength, a feature that allows science to self-correct and improve over time. When evidence contradicts established theories, science eventually adapts, though not always quickly or smoothly. The resistance to new ideas is often fierce, and overturning established frameworks requires compelling evidence and persuasive arguments. But it does happen, and the history of geology itself demonstrates this. Continental drift was ridiculed when first proposed in the early 20th century. The idea that continents moved seemed physically impossible, and the mechanisms proposed to explain it didn't withstand scrutiny. For decades, the hypothesis languished on the margins of geological thinking. Then, in the mid-20th century, new evidence from ocean floor mapping, paleomagnetic studies, and other sources began to accumulate. The theory of plate tectonics emerged, providing a robust mechanism for continental movement. Within a decade, the scientific consensus shifted completely. What had been dismissed as impossible became the central organizing principle of geology. The Silurian hypothesis might follow a similar trajectory, or it might not. It might remain forever speculative, a thought experiment that never finds empirical support. The key is maintaining openness to evidence while requiring that evidence to meet rigorous standards before accepting extraordinary claims. As we contemplate these questions in this quieter space, the urgency of finding answers diminishes. What remains is a kind of meditative awareness of deep time, of our small place within it, of the vastness of what we don't know compared to what we do. This awareness doesn't lead to nihilism or despair. Instead, it can cultivate a sense of wonder at the sheer scope of Earth's history and the processes that have shaped our planet. Think about the journey that every atom in your body has taken. The hydrogen formed in the first few minutes after the Big Bang. The carbon, nitrogen and oxygen forged in the hearts of massive stars and scattered across space when those stars exploded. These atoms drifted through interstellar clouds, eventually coalescing into the disk of gas and dust that formed our solar system. They became part of Earth, cycling through rocks and water and air, through countless organisms, before temporarily assembling into the form reading these words. Every atom has a history that spans billions of years and encompasses the full sweep of cosmic evolution. You are, quite literally, made of stardust that has been recycled through geological and biological processes for eons. Your existence represents a temporary configuration of matter that will eventually disperse back into Earth systems, your atoms becoming parts of other organisms, other rocks, other processes. This perspective places the question of ancient civilizations in a different light. Whether we're the first or the latest in a long series, we're all temporary configurations of matter and energy, brief sparks of self-awareness in a universe that mostly isn't aware of itself. Our technologies, impressive as they seem to us, are ultimately just sophisticated ways of rearranging matter and energy. We split atoms, but so do natural nuclear reactors under the right geological conditions. We synthesize complex molecules, but chemistry happens with or without conscious direction. We alter our planet's atmosphere, but so do photosynthetic bacteria, volcanic eruptions and asteroid impacts. What makes us potentially special isn't that we can do things nature can't. It's that we can understand what we're doing, can contemplate our place, in the larger patterns, can ask questions about meaning and purpose and legacy. This capacity for reflection, for stepping back and examining our own existence from multiple perspectives, might be our most distinctive feature. And in exercising that capacity, in asking whether others might have possessed it before us, we're engaging in a very human activity, trying to understand our place in a universe that doesn't offer easy answers to our deepest questions. The rocks can tell us about chemistry and climate, about the movements of continents and the extinction of species, but they can't tell us what those things mean, can't provide the interpretive frameworks that transform data into understanding. We bring the frameworks, we bring the questions and the curiosity and the drive to make sense of patterns in nature. And in doing so, we shape what we're capable of discovering. The Silurian hypothesis exists because two scientists wondered what signatures modern civilization would leave, and then asked whether similar signatures might exist from earlier times. They brought that question to the geological record, and the record responded with ambiguities and possibilities rather than clear answers. Those ambiguities are themselves informative. They tell us about the limits of preservation, about the challenges of interpreting fragmentary evidence, about how much of Earth's history remains uncertain despite our sophisticated analytical tools. They remind us that some questions might not have definitive answers, at least not with our current capabilities and perhaps not ever. This lack of certainty might frustrate those who want clean resolutions to every question, but it also creates space for continued investigation, for new approaches and techniques, for the possibility that future generations might see patterns we've missed. The story of Earth's history isn't finished being written. Each new discovery adds details, revises earlier interpretations, raises new questions that previous researchers couldn't have anticipated. We're participants in an ongoing conversation with the past, mediated through rocks and chemistry, and the patient work of extracting information from degraded and fragmentary records. Sometimes the past speaks clearly. Sometimes it whispers ambiguously. Sometimes it remains silent no matter how carefully we listen. The silence around ancient civilizations might be the silence of absence, confirmation that we truly are the first, or it might be the silence of insufficient sensitivity, evidence waiting to be discovered by techniques we haven't developed yet. Or it might be a deeper silence, one that acknowledges some questions extend beyond our current capacity to answer definitively. Learning to sit comfortably with this uncertainty, to hold questions without demanding immediate answers, is its own form of wisdom. It allows us to remain curious without becoming credulous, to explore possibilities without losing our critical faculties, to imagine alternatives without abandoning our commitment to evidence and rigorous thinking. The universe is under no obligation to organize itself according to our preferences or our intuitions about what should be true. Reality is what it is, independent of our wishes or beliefs. Our job as thinking beings is to observe carefully, reason clearly, and remain humble about the limits of our knowledge. We can make provisional conclusions based on available evidence, while acknowledging that new evidence might overturn those conclusions. This is the space where the Silurian hypothesis lives, in the territory between speculation and knowledge, between imagination and evidence, between what we can currently determine and what might someday become determinable. It asks us to look at familiar patterns with fresh eyes, to consider whether our interpretations might be incomplete, to remain open to surprises while maintaining appropriate skepticism. And perhaps most importantly, it asks us to think about our own legacy, about what traces we're leaving, about how future investigators might interpret the signatures we're creating. Are we being wise stewards of this planet, or are we burning through irreplaceable resources in a brief flare of unsustainable consumption? Are we building something that can last, or are we creating conditions that will lead to our own collapse? These aren't just philosophical questions, they're practical ones with immediate relevance to choices we make every day. The geological perspective that the Silurian hypothesis encourages, this long view across millions of years, can inform how we think about sustainability, about resource use, about our responsibilities to future generations. If we want our civilization to persist, to leave a legacy of something more than just chemical anomalies and scattered microplastics, we need to think in geological terms about the consequences of our actions. We need to ask not just what benefits us in the short term, but what creates lasting value across timescales that dwarf human lifespans. This long-term thinking doesn't come naturally to us. We evolved to focus on immediate threats and opportunities, not on consequences that won't manifest for thousands or millions of years. But our technology has given us the power to create changes that will persist for geological timescales, and with that power comes the responsibility to think carefully about how we use it. The silence of the rocks regarding previous civilizations might be teaching us something important. That civilizations leaving loud signatures in the geological record might be civilizations that didn't last very long. The sustainable ones, the ones that figured out how to persist across deep time, might be precisely the ones that left the faintest traces, the ones we'd have the hardest time detecting. If that's true, then our current trajectory, burning fossil fuels and scattering synthetic materials and altering global chemistry at unprecedented rates, might be the trajectory of a short-lived civilization. We're creating a bright signature that will be easily detectable for millions of years. But brightness in the geological record might correlate inversely with longevity as a civilization. The alternative would be to transition toward technologies and practices that work with Earth's systems rather than against them, that can continue indefinitely without depleting resources or degrading environments. Such an approach would leave fainter geological traces, but might allow our civilization to persist across timescales currently unimaginable to us. This is the deeper lesson of the Silurian hypothesis, perhaps more valuable than any specific answer about whether ancient civilizations existed. It encourages us to think about time differently, to consider our actions from the perspective of deep future observers who might someday examine our geological legacy, to ask what kind of ancestors we want to be to whoever or whatever comes after us. The rocks will remember us, one way or another. The chemistry we're altering, the materials we're dispersing, the species we're driving to extinction, all of these will leave permanent marks in Earth's geological record. Future scientists, whether human or otherwise, will be able to identify our era clearly. The question is, what story those signatures will tell? A story of wisdom and foresight, or a story of short-sighted excess? A story of a civilization that learned to live sustainably, or a story of one that burned bright and brief before collapsing under the weight of its own environmental impact? We're writing that story now, in every choice we make about energy and resources and technology. The Silurian hypothesis holds up a mirror that reflects our current actions across millions of years of future time, asking us to see ourselves as future geologists might see us, to consider whether the legacy we're creating is one we can be proud of. And in this contemplation, in this slow consideration of deep time and distant consequences, perhaps we find a kind of peace with uncertainty. Not all questions have answers, not all mysteries get solved. Some ambiguities persist despite our best efforts to resolve them, and that's okay. The universe contains more mystery than we can ever fully comprehend, and our role isn't to eliminate all uncertainty but to navigate it wisely. The silence speaks if we know how to listen. It tells us about humility, about patience, about the long arc of time that extends far beyond our brief lives. It reminds us that we're part of something larger than ourselves, participants in processes that operated long before we arrived and will continue long after we're gone. Whether we're Earth's first technological civilization or merely its latest, we're here now, thinking these thoughts, asking these questions, trying to understand our place in the vast sweep of planetary history. That itself is remarkable, a moment of self-awareness in a universe that mostly isn't aware of itself. And in that awareness, in that capacity to wonder and question and imagine, we find something worth preserving, worth passing forward, worth encoding into our geological legacy as more than just chemical signatures and scattered debris. The rocks will hold our secrets, just as they might hold the secrets of others who came before. Time will tell which stories they're keeping, even if we never learn to read them all. And in the meantime, we continue the work of investigation and discovery, asking questions, gathering evidence, building understanding one careful observation at a time, always aware that the horizon of knowledge extends infinitely beyond wherever we currently stand. This is where our journey through the Silurian hypothesis comes to rest, not in definitive conclusions but in expanded awareness, not in answers but in better questions, not in certainty but in the recognition that uncertainty itself can be a teacher if we approach it with curiosity and humility. If you found value in this exploration of deep time and ancient possibilities, consider subscribing to join us on future journeys through science's most intriguing questions. Your support helps us continue creating thoughtful content that examines the boundaries of human knowledge,